Good afternoon. I'm Katherine Blundell, Gresham Professor of Astronomy, and I'd like to welcome you to Lecture 6 in this series on cosmic vision. Cosmic vision is all about how we see what's out there, how we investigate it, how we analyse it. And that's been the theme of this whole academic year's Gresham Lectures in Astronomy. This series began with a lecture called Watching the Radio. And this discussed the idea that we can explore outer space by making use of long wavelength light, the very low energy, long wavelength part of the electromagnetic spectrum. The importance of this particular waveband within the electromagnetic spectrum is that radio telescopes observing at, say, centimetre wavelengths show a very different picture of what is going on in the universe. And here is a beautiful example of a radio galaxy, a quasar-type object, ejecting jets into outer space. And I discussed the importance of this and the prevalence of this in that lecture. The second lecture was entitled Attentive Eyes. And this explored just how much we can learn with our own human eyes. This, of course, necessitates observing in the optical waveband of the electromagnetic spectrum, in which we can see where fusion is taking place in the universe, where we see stars, and also, excitingly, planets. I'm showing here a movie of Jupiter and Saturn as they did their flypast just last December. Although this particular image is obviously taken with a camera, it's made at the same wavelength that our human eyes are receptive to. The wavelength of these images that I'm showing you in this movie are less than 1,000th of 1 millimetre. Historically, over the past few millennia, human eyes, attentive human eyes, have captured a whole range of cosmic behaviour. And witnessing fireworks, which I covered in my third lecture in this series, really focused on some of the spectacles that happen only occasionally in cosmic history, such as the close flypast of comets, as shown here, or the explosion of a supernova. Still focusing on optical light, but now splitting up the light rather than thinking about images with light, was my fourth lecture on unravelling rainbows. Rainbows are the word that we give to a spectrum, and spectroscopy is the study of light that has been split up. And one of the important things that this brings to us is dynamics, how things move, how they attract one another, how they orbit around one another. Lecture 5, entitled Fast and Furious, focused not on light from some part of the electromagnetic spectrum, but on massive particles accelerated in extreme environments in outer space. By massive here, I mean particles like protons, or maybe the nuclei of some of the heavier elements, such as nitrogen or iron. Cosmic rays give us very poor spatial resolution. We don't get images of the cosmic ray universe. But cosmic rays do tell us about extreme energy environments in the universe. And they tell us a lot about how these extreme environments actually work. And so in this final lecture on cosmic vision, I want to focus on the question, what other messengers might there be in outer space besides different parts of the electromagnetic spectrum, besides the massive particles that comprise cosmic rays? By what other means might we be able to learn what is going on in outer space? And so the title of today's lecture is Space-Quakes. These are messages through the medium of space-time itself. This is a very new kind of astronomy. Forget the millennia of astronomical discovery through attentive human eyes. This field of astronomy, gravitational wave astronomy, only really took off just over 5 years ago. So to begin to explain what all this is about, we need to consider what we mean by space-time itself. What is space-time? Space-time is what we are embedded in. People talk about the fabric of space-time. And what's important to appreciate about space-time is that it responds to the presence of mass. Where there is mass present, there will be curvature in the local space-time, compared to no curvature if there were no mass present. The significance of curvature in local space-time is that if a massive particle should wander by, the path it moves along will be different precisely because the space-time through which it is moving is curved. This fits together because we would expect that because of gravitational attraction and conservation of angular momentum that we have met previously, the path of that massive particle would be curved. So the curvature of space-time can be regarded as telling the mass how to move, what path to actually move along. Space-time is curved when you are close to mass. But even for a mass like planet Earth, the effect is hardly noticeable here on Earth, although it does lead to effects which are important to take into account when using your GPS for navigation. This works because you're timing signals from satellites. Those further from Earth are going at a slightly different rate from the wristwatch on your arm, here on Earth, I presume. The effects of curvature on space-time become much more important if you are talking about a much more massive object than planet Earth, such as a large, massive, compact star such as a black hole or a neutron star. Albert Einstein said we should not think of space and time as separate, but as one single entity that we now refer to as space-time. Space-time is a four-dimensional structure that conceptually supersedes the more familiar 3 dimensions of space and the 1 dimension of time. And the important thing to realize, as we've seen, is because space can curve in the presence of mass, space-time is not rigid. And although space-time is not rigid, it is stiff, as we will see later on. John Wheeler, latterly of Princeton, is the person who coined the term black hole. And he describes the close connection of the curvature of space-time with gravity and how matter responds to the curvature of space-time in the following epithet. Space-time tells matter how to move. Matter tells space-time how to curve. And it's this latter bit that I want to focus on. Matter tells space-time how to curve. How might the distribution of matter change? If you had 2 black holes merging into 1 black hole, this would cause a different distribution of mass, hence a varying curvature, hence ripples in space-time might be expected. And in fact, these ripples in space-time are better known as gravitational waves. Einstein's general theory of relativity enables us to calculate a prediction for what the gravitational waves would look like. And a prediction, followed by testing, is a big part of what science is all about. So just how do you go about testing whether space-time is actually rippling or not? We begin by making careful predictions from general relativity about the calculation of the effect that 2 black holes orbiting one another and ultimately merging have on one another. In such a calculation, as I've said, if the distribution of matter changes, space-time is indeed expected to curve differently. If the distribution of matter changes, space-time will curve differently. What would ripples in space-time actually look like? I'm going to turn now to one of my predecessors as Gresham Professor of Astronomy, pictured here Sir Christopher Wren. The effect I'm going to show is rather exaggerated, but this is a bit like what it would look like if a gravitational event had occurred within London, really close by to Sir Christopher Wren. As we'll see later, a typical gravitational wave event might take place 1 billion light years away from Earth. So in reality, the gravitational wave events that were taking place when Gresham College was first founded wouldn't have been noticed by Sir Christopher Wren or any other human without advanced sensitive information, such as the instrument that I'm now going to describe, LIGO, which is responsible for the initiation of the wonderful new field of gravitational wave astronomy. So what is LIGO? LIGO is an instrument for measuring gravitational waves, for measuring these ripples in space-time. It's a type of instrument that we call an interferometer. Signals are received at more than one location and then interfered with one another, we say correlated with one another, to determine the reality and the nature of the signal, whether it's caused locally to a given detector, one or other detector, or whether it's extraterrestrial and therefore of great interest. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And there are 2 sites. LIGO Hanford is in the southeastern part of Washington State in the United States of America. 3,000 kilometers away from this is LIGO Livingston, which is located in Louisiana. Both are in sparsely populated places, as long as you're talking about humans. They're not sparsely populated in terms of trees. And this is for the same reason that you don't build an optical observatory inside a big city. You want to really minimize the possibility of a polluting signal. Each detector is sensitive, very sensitive, to effects local to them, such as lorries driving past, seismic events such as an earthquake, even a farmer ploughing a field. But the point is that by having detectors far apart from one another, they will not feel the same local vibrations. By comparing the signals from both sites, it is possible to ignore the effects that are only located at one location and not the other. And then what you do is search for identical signals that occur at the same time, but in 2 different places. So what I'm showing now is a picture of the two LIGO detectors, Hanford and Livingston, together with a movie of what each detector experiences when a gravitational wave passes by. Much exaggerated, of course, but I hope it illustrates the principle. You have 2 perpendicular arms which respond differently to the ripples in space-time as they pass by. And understanding this signal and then correlating it with the other site, 3,000 kilometers away, is the key to determining whether a signal, an extraterrestrial signal corresponding to a genuine ripple in space-time, has been detected or not. This is an overhead view of the Hanford Observatory. What each observatory needs to be able to detect is very, very tiny movements. By tiny here, I mean 1/10 billionth of the wavelength of light. I mentioned earlier that the typical wavelength that human eyes are sensitive to is less than 1,000th of 1 millimeter. And the movements that these gravitational wave detectors need to be sensitive to is 1/10 billionth of that. So the instrument is designed as follows. To detect movement in space-time, you send in a laser beam, you split the beam, and you send it along the 2 perpendicular arms shown here. The arms are long meaning 4 kilometers, because you're trying to pick up a very small fractional change. So the idea is that you send in a laser beam, shown here on the right. You split it at a beam splitter in the center. And then these 2 perpendicular travelling beams of laser light get reflected on an end mirror at the end of each arm and travel back again. In the absence of any vibration, be it local or extraterrestrial, these reflected beams will combine exactly in phase, or at least with a fixed phase relationship. And a photodiode, which is just a detector, will register that. But if either arm changes in length, even subtly, then they won't recombine at the exact same time with the exact same phase. And it's the nature of the change in arm length that can be calculated. This signal, when combined with the signals received by the other interferometer 3,000 kilometers away, makes it possible to say whether the change in arm length arises from a local effect or an extraterrestrial effect. This movie, I think, will explain even more clearly what's going on. Light from the laser is split at the beam splitter, and the two perpendicular paths of light each get reflected at their mirror. On returning to the beam splitter, they then recombine and head towards a detector with a fixed phase relationship. By digitizing and recording the specific patterns of signals that hit those detectors, it's then possible to analyze what is observed and compare those data to computer models of predicted gravitational wave signals that are generated from calculations from general relativity. When gravitational waves pass through this device, they cause the lengths of the two arms to stretch and squeeze by different amounts, infinitesimally small and obviously exaggerated here in this movie for visibility. It's this movie that causes light at each detector to flicker. That's the signal that gets measured. And so LIGO is able to undertake detection experiments, which I think you'll agree can reasonably be described as challenging. The ripples in space-time that LIGO is designed to observe are tiny. The fractional change, known as the strain, which needs to be measured, is as small as 10 to the power of minus 21. That's the ratio of the change itself divided by the distance over which the change is measured. So over 4 kilometers, the actual change in arm length is 10 to the power of minus 15 centimeters. To help you calibrate how small that distance is, it is 1% of the size of a proton. It is 10 to the power of 11 smaller than the wavelength of light, which, as I said earlier, is pretty tiny. So how did LIGO come about? Well, it was instigated quite a long time ago now, in the early 1990s, when George Bush I was president of the United States. Augusto Pinochet was the president of Chile. Apartheid was still reigning in South Africa. John Major had just taken over from Margaret Thatcher as the Prime Minister in the UK. It may feel like a long time ago, and it was. And so it took the best part of 2 decades to succeed at measuring the distortions in space-time due to changes deep in outer space. Sometimes science does take a really long time to succeed. There are many other problems in science which take decades, not merely years, to solve. Superconductivity was discovered in 1911, but we didn't get superconducting magnets until the 1960s. And MRI scanners which use these only came into hospitals a couple of decades after that. Fusion is another example. It was recognized as a potential source of power in the 1940s, and we still haven't made it practical. Sometimes fusion is mocked as being always 30 years away, but how long a big, bold scientific endeavor can take also depends on whether the requisite funds and resources are in place. If not, it will take longer than planned. We do know, however, that fusion has been working well in the universe since shortly after the beginning of time. So there is very much hope we will succeed in sustaining it here on Earth. Back to LIGO, the first big science run in 2009 to 2010 saw nothing. But then an advanced interferometer was installed at each site, and half a decade after that first big science run, a new experiment began in September 2015. And at this point, I want to ask a question. When does 36 plus 29 equal 62? It's maybe a bit of a puzzling question because it might seem that there's a delta of 3 missing from this. But the answer to this question is the 14th of September 2015. And the units of this equation are solar masses, masses of our sun. What am I talking about here? And what's the connection with LIGO? Well, these are the masses of the black holes that were involved in that first gravitational event. The initial 2 black holes that were involved had a mass of 36 solar masses for the more massive one, 29 solar masses for the other one. And when they were merged, their total mass was 62 solar masses. 3 solar masses was radiated away in energy as gravitational waves. This event was observed by both LIGO detectors, and the event is known as GW 150914. It's date stamped to give us the name. So I want us to think a little bit about that 3 solar masses of energy equivalent radiated away as gravitational waves. And I want us to consider the question, when is 3 a large number? 3 is a large number when the units are masses of our sun. 3 solar masses is 300% of the mass of our sun. How much energy is radiated by the sun? At a distance away from Earth of 150 million kilometers, if you are standing on the equator of our rotating planet, then you, a human, will cook. We get a lot of energy from our sun, even though we're rather a large distance away from it. Now, the sun has lost 0.03% of its mass via electromagnetic radiation, i.e. light, since its formation 4.5 billion years ago. Radiating away 3 solar masses of energy as gravitational waves is equivalent to 10,000 times the amount of energy radiated as light from our sun in the last 4.5 billion years. But this gravitational wave event did that in less than 1 second, less than 1 second. Now, only a very tiny distortion was actually measured here on Earth, a relative change in distance of 10 to the power of minus 21, because space-time is very stiff. It is 10 to the power of 22 times stiffer than steel. So what did the actual measurement look like? Well, these are the data that were actually received at Hanford and at Livingston. The signals came from these 2 merging black holes, each approximately 30 times the mass of our sun, located over 1 billion light years away. The top 2 plots show data received respectively at Hanford and at Livingston. And overlaid on each data stream, you can see in a very thin line the predicted shape for the waveform expected from 2 merging black holes with the corresponding masses. These predictions come from Albert Einstein's equations in his general theory of relativity. So what's plotted on the vertical axis in each case is this quantity called the strain, the relative change in length. What's plotted on the horizontals is time, and the units are seconds, and the separation of the tick marks on the axis are 0.05 of a second. As the plots reveal, the LIGO data that was actually recorded very closely match Einstein's predictions. The bottom of the three plots compares data from both detectors. The Hanford data have been inverted for comparison due to differences in the orientations of the detectors at the two sites. And the data were also shifted to correct for the travel time of the gravitational wave signals between Livingston and Hanford. The signal reached first Livingston and then travelling at high speed, more of what that speed is later, arriving at Hanford several thousandths of a second later. As the plot demonstrates, both detectors witnessed the same event, confirming the detection. In this animation that I'm going to show you now, gravitational waves are sent out from a simulated pair of colliding black holes, and the gravitational waves have been converted to sound waves, as you'll hear. So on September the 14th, 2015, LIGO observed gravitational waves from the merger of two black holes, each of order 30 times the mass of our sun. The incredibly powerful event, which released more than 50 times more energy than all the stars in the observable universe, lasted only fractions, tenths of 1 second. In the first two runs of the animation, the sound wave frequencies exactly match the frequencies of the gravitational waves. But in the second two runs of the animation, the sounds are played again at higher frequencies that are perhaps better suited to the human hearing range. And the animation ends by playing the original frequencies again twice. What you'll hear is as the black holes spiral closer and closer in together, the frequency, the pitch of the gravitational waves increases. And these increases in frequency are known as chirps, because some events that generate gravitational waves sound like a bird's chirp. So here we go. Let's listen to the animation. Now let's view a more visual simulation of the event that was going on. All of these simulations and data visualizations are due to the LIGO lab, based not just at the LIGO stations, but also at Caltech and MIT. So here we go. This is a simulation of extreme space-time. So initially we have the two black holes orbiting one another. Space-time is curved due to the presence of each mass. They continue to orbit one another, gradually spiraling in, that frequency gradually increasing as they get closer to one another. And as they inspiral, you can see the deep potential well, the deep curvature in space-time beginning to merge. The arrows indicate the direction of gravity. So the speed of the simulation is slowed down just to be able to take it in, but in reality, this process would be going faster and faster. So the movie is frozen just to give us a sense of the coalescence of the two black holes into the one. From that coalescence event, the two black holes become one, and ripples from that in space-time emanate from that event, traversing the universe. This particular simulation was thanks to the Simulating Extreme Spacetimes project And I've left the URL there so that you can look up and see some of the other simulations that they've done. They are indeed fascinating. I'd like to now compare gravitational waves and electromagnetic waves. Gravitational waves and electromagnetic waves both tell us about outer space and what's going on, the dynamical events in outer space. But let's understand some of these detailed differences a little more. Gravitational waves occur due to the bulk motion of mass. It's when you've got asymmetric motion, when two black holes are merging or two neutron stars are merging into one another. The movement of mass causes differently curving space-time, and that is manifested as waves or ripples. Electromagnetic effects, on the other hand, are due to the effects of many different particles moving together. For example, electrons being accelerated or in a very, very hot plasma. A lot of the details of why we see radiation, electromagnetic radiation, in a way that depends on the temperature of the radiating body was explored in my lecture on cosmic vision, unraveling rainbows. A different aspect of the comparison of gravitational waves and electromagnetic waves is the fact that gravitational waves interact very, very weakly with pretty much everything else. What's bad about this is it makes them very hard to detect, which is why you have to go to the lengths that the LIGO organization did. It's why it took those decades of very careful, very painstaking development of the necessary engineering in those detectors. But the good thing about the very weakly interacting nature of gravitational waves is that we get a pristine view of the universe. This is in contrast with electromagnetic waves. These scatter very many times en route from the distant galaxy or whatever it might be, en route to our telescopes here on Earth. And we always have to factor that in to our understanding of what we think we're seeing when we make optical or radio observations. Another more significant difference between gravitational waves and electromagnetic waves is that gravitational waves are not very spatially resolved. The wavelengths are absolutely enormous, way bigger than the size of the solar system. And so what gravitational waves bring us is dynamical information rather than spatially resolved images. There's almost a better analogy of gravitational wave astronomy with spectroscopy of the kind that I talked about in my lecture on unraveling rainbows. Electromagnetic waves, on the other hand, give us richly detailed images of the distribution of radiating matter in outer space. This particular image here, revealing resolved light of the beautiful Tarantula Nebula in the southern sky, is telling us about the distribution of hydrogen atoms in this nebula. The wavelength is less than 1/1000th of a millimeter. This image, it tells us about the distribution of that material that's responsible for emitting the light, but it, on its own, doesn't tell us about the dynamics. Spectroscopy can do that for us, as discussed in my Unraveling Rainbows lecture. Gravitational wave astronomy can't do anything of the kind for us. As I mentioned, gravitational wavelengths are very, very long, which makes imaging impossible. Now, the analogy is not perfect, but receiving gravitational waves can be compared with listening to the radio in the sense of detecting vibrations rather than watching TV. With electromagnetic waves, the wavelengths that we're talking about, less than 1/1000th of a millimeter in the case of optical wavelength, is vastly less than the size of the source responsible for that radiation. So now back to some gravitational wave events. And I'm talking about one now that occurred about 3 months after that first detection that I talked about earlier. This one is known as GW 151226. It was the second definitive observation of a merging binary black hole. But for this particular gravitational event, it wasn't just LIGO that was involved, it was another gravitational wave observatory known as Virgo. Virgo is part of the European Gravitational Observatory. It's another interferometer, really rather similar to those of LIGO, again designed to detect gravitational waves as predicted by Einstein's general theory of relativity. Virgo is an interferometer, again, very similarly designed to the LIGO interferometer. Its mirrors and its instrumentation are suspended. The laser beam similarly operates in a vacuum, just like LIGO. This instrument's two arms are 3 kilometers long rather than 4 in the case of LIGO, and it's located near Pisa in northern Italy. Virgo is part of a scientific collaboration of laboratories from 6 countries: Italy, France, the Netherlands, together with Poland, Hungary, and Spain. And it collaborates with LIGO because having 3 detectors on different parts of the surface of the Earth significantly improves our ability to detect the direction that the signal is coming from. So I'm going to show you now a visualization of the data from GW 151226. It was detected on Christmas Day 2015 in terms of local time at LIGO in the US, but to avoid time zone ambiguity, the name derives from the timestamp appropriate to UTC, that is the Universal Coordinated Time Zone, the successor to Greenwich Mean Time, also known as Zulu Military Time. The masses of this inspiraling black hole were 14 and 7.5 solar masses. And on merging, about just 1 solar mass was radiated away, 1/3 of the energy radiated in the first ever detected gravitational wave source. The location on the sky was still relatively poorly constrained, but it was another strong indicator that there is a significant population of black holes in binaries in the universe, with masses at least 10 times the mass of our sun. So the increasingly familiar characteristics of an inspiraling black hole binary pair are that ripples are detected in space-time and their wavelengths gradually decrease, their frequencies gradually increase as the coalescence actually happens following increasing inspiraling of the 2 black holes. Here is another visualization of that exact same event, thanks again to Caltech and MIT and the LIGO lab. This visualization is showing the manifestation of the ripples in space-time on starlight. It comes obviously from a computer simulation of 2 black holes as they spiral and collide and merge. Time in this simulation has been slowed down by a factor of 100. The positions of the stars appear to be warped as space and time, which we now know as space-time, themselves become warped due to the changing distribution of matter. The path that light takes becomes curved, and this is a phenomenon known as gravitational lensing. The ring around the black holes is known as an Einstein ring. And within this radius, the Einstein radius, light from all the stars in a small region behind the black holes becomes smeared via gravitational lensing into that ring. And so now I'm going to describe another gravitational event. There have been quite a few others, which I won't particularly go into today. But this one, GW 170817, was highly significant because it heralded the true beginning of something I'm going to describe as multi-messenger astronomy. There were a number of differences about this gravitational event, differing from the previous ones involving the merging of a pair of black holes. This one was the first observation of merging neutron stars. And its gravitational wave signal was significantly different from the gravitational wave events involving black holes. Its duration was significantly longer than all the other events that had been detected to date, as I'll now illustrate with another visualization from LIGO, Virgo, and the University of Oregon, thanks to Ben Farr. So the horizontal axis is representing time. In GW 170817, about 100 seconds before the neutron stars merged, they were separated by about 400 kilometers and completed about 12 orbits every second. With every orbit, gravitational waves forced the stars closer together as energy was being radiated away. As those orbits shrink, the stars move faster and faster, and the strength and frequency of the gravitational waves increases. This slow shrinking of the orbit is called an inspiral, and the increase in frequency is, as I've said, called a chirp. The process accelerates until the stars merge and form a single remnant. What was really special about GW 170817 is that it was the first event that heralded true multi-messenger astronomy. It wasn't just a gravitational wave event, it was also an electromagnetic event. It was, as I said, the first observation of merging neutron stars. That's why the signal persisted. It was detected not just by that means in gravitational waves, but also in electromagnetic waves. The first electromagnetic signal from this exciting event was picked up at gamma ray wavelengths. Gamma rays are like X-rays, only even more so, even shorter wavelengths, even more energetic photons. And it was the gamma ray burst monitor on board the Fermi satellite that enabled this detection. What I'm showing you here is a depiction on the celestial sphere in a particular geometric projection of where the different instruments, electromagnetic in the case of the Fermi satellite and the integral satellite, sensitive to very high energy electromagnetic waves that were responsible for the purple and the grey regions on this figure, respectively. And the green event was actually the localization due to LIGO and Virgo. At the very center of the green region is located a galaxy known as NGC 4993, which is what played host to the source of those gravitational waves detected by LIGO and Virgo, and the electromagnetic event that was picked up by the Fermi satellite and the integral satellite, sensitive to very high energy X-rays, gamma rays. This event occurred near Hydra in the night sky. Having been alerted by Fermi and by integral, optical and radio telescopes all over the planet were able to slew and investigate and really localize the source of these gravitational waves and electromagnetic waves. This figure here shows what we call the light curves. In other words, how the electromagnetic signal changes with time for the Fermi satellite in two different wavelength bands or energy bands, slightly lower energy in the top plot, slightly more energy in the middle plot, and then the light curve from the integral satellite at in between energies. The very bottom plot is showing us that of the gravitational wave signal. And you can see the vertical black bar is showing where the merger took place according to when the gravitational wave signals were received. The grey vertical line shows the onset of the signal that triggered the gamma ray alerts from the Fermi satellite and from the integral satellite. So actually, this gravitational wave event was actually what is known as a gamma ray burst, which is what the Fermi and the integral satellites are designed to detect. This gamma ray burst was hosted in the galaxy NGC 4993. It was absolutely remarkable that a gravitational wave source should be accompanied by such a slender time interval later by an electromagnetic event, which turned out to be a gamma ray burst. This has been wonderful for both the study of gamma ray bursts, which are wonderfully energetic phenomena in space. Gamma ray bursts give rise to jets of relativistic plasma, similar to those that I talked about in my lecture on black holes and jets from black holes in the third lecture of my series entitled Cosmic Concepts. That particular lecture was entitled The End of Matter, ? Not only did this dual gravitational wave event and electromagnetic gamma ray burst event have important implications for the very nature of gamma ray bursts, precisely because it confirmed that the progenitor of a gamma ray burst is the merging, the coalescence of two neutron stars previously in orbit around one another. But it had significant implications for fundamental physics and for cosmology. The slender offset shown in this figure between the merger of the two neutron stars as received by the gravitational wave observatories LIGO and Virgo, followed by the main event in gamma rays, is very significant. Over the cosmological distances that we're talking about out to this galaxy, the various optical telescopes involved in performing these follow-up observations were able to deduce that the distance to this object from Earth is in excess of 1 billion light years. This paper, one of a number describing this amazing event by Abad et al., published in the Astrophysical Journal Letters, showed that the difference in speed at which gravity travels and the speed of light travels that I described in my inaugural lecture on faster than light corresponds over that enormous distance of over 1 billion light years to a difference in speed of less than 10 to the minus 15. Another beautiful result in their paper reporting the combination of gravitational waves and an electromagnetic spectacle is, as I said, the astrophysical result that the progenitor of a gamma ray burst is the merger of two neutron stars in combination with this amazing result for cosmology that gravitational waves travel essentially at the speed of light. Even that difference of 1.7 seconds could be due to some local astrophysical effects at the newly merged black holes as the jets that may give rise to the gamma rays that are detected by the Fermi satellite and the integral satellite as that jet actually forms. And so this is truly important for cosmology as well. Thus far, the heroic detections and analyses of gravitational wave events are completely in keeping with the predictions of Einstein's general theory of relativity. And I do hope that in this lecture, as with the whole series of 6 lectures entitled Cosmic Vision, how do we obtain vision and information on the cosmos? I truly hope that this has expanded your cosmic horizons and broadened your vision. Take care, keep well, and keep looking up.